Hello everyone. So today we're going to start on 13.3, which is talk about basically solving a system of differential equation, but a system is called a non-homogeneous system. So what does that mean? So well, the system that we have been doing so far are basically homogeneous system, and the definition is the following. Oops. Let's say we're given a system of differential equation. If it can be written in the form of d vector x over dt equal to a of t vector x, then it is called a homogeneous system. So that basically is the same type of differential equation that we have been dealing with. Okay. Now, what happened to a non-homogeneous system? Well, if it can be written in the form of d vector x over dt equal to a of t x vector x. Yeah, that doesn't look like a vector. Vector x plus b vector b of t. Now, of course, here vector b of t cannot equal to the 0 vector, because if it does, then we will basically have a homogeneous system. Then it is called a non-homogeneous system. So we have learned so far from 13.1 and 13.2 basically how to solve a homogeneous system using eigenvalue, eigenvector in 13.1. And in 13.2, we would use matrix exponential, especially when we run into the scenario where the matrix A actually has repeated eigenvalue, and therefore we cannot use eigenvalue, eigenvector to solve the system. So now comes the big question. What if we have a non-homogeneous system with the actual vector b of t? How would that cause an issue when we try to find the solution to it? So we're going to try to figure that out. But before we do that, I do need to define something first that will help us set up this type of problem. And that is definition 13.3.1, which states the following. Let's say you're given two matrices, or actually two matrix functions. Let's say a of t and b of t, so that their product is a of t, b of t. Now here, of course, notice that one thing I didn't do, which I normally would do whenever we define a matrix, is to define the dimension of this matrix. So here we actually don't really care the dimension of the matrix as long as this is true. As long as we can form their product, AB. And we do want the product to be multiplied in this direction. So therefore, B of t, A of t may not be defined. But since A and B are arbitrarily defined anyway, it really doesn't matter. We don't really have to define it both directions. Now that we have a product between these two matrices, what I want to figure out is, what happens if I want to take the derivative of this thing? So essentially what we're learning is, technically speaking, the product rule for matrix multiplication differentiation. So what would be the derivative is? Well, let's find out. The derivative of their product, once again, we assuming that the way the dimension of these two matrices would be, it would work out to form a product. So the product is definitely defined. So the derivative of the product is actually given by the formula if you take the derivative with respect to t of a of t, b of t, it would basically equal to the derivative of a of t multiplied by b of t plus a of t multiplied by derivative of b of t. This expression can be written backward, meaning that you can put a of t derivative of b of t plus derivative of a of t b of t. That is okay because addition between two matrices is commutative. However, what you cannot write is this. Note. The derivative of a of t b of t is not equal to this. Okay, why? Because to write b first then a in this multiplication will require the product that we start with when we take a derivative have b in front. Otherwise, it will require somewhat a flip-flop of the multiplication between a and b, which we know is not true in matrix multiplication. So therefore, be very important, and when you're dealing with this formula, is that you cannot flip-flop the order of the two functions when you multiply. It will result in that your operation is invalid and your derivative will be incorrect. So make sure you pay attention to that. So now that we have this definition under a belt, now we can talk about how do I form a solution to a non-homogeneous system of differential equation. So that would be theorem 13.3.2, which states the following. Let's say we're given the vector equation, vector differential equation. So when I say vector differential equation, that's basically mean a system of differential equation. D vector x over dt equal to a vector x plus vector b of t. And here is very important, where A is a constant matrix. So we can't deal with A being not a constant matrix, not yet, but we will. And in this case, vector b of t is a continuous function. Continuous like vector function because it's supposed to give out a vector. The solution to this differential equation, the general solution to this vector differential equation will be in the form of So here's the formula you need to memorize. Vector x is equal to e to the ta integral of e to negative ta vector b of t dt plus e to ta vector c with a constant vector c. So if you look at this expression right here, notice it might look complicated, but it's actually nothing that you haven't seen before, in the sense that you know how this structure in a non-homogeneous differential equation, you understand that the solution is a combination between two things. It's a composition between a homogeneous solution and a non-homogeneous particular solution. And as a matter of fact, this is exactly what we have here. You should probably identify that this is, technically speaking, our homogeneous solution, because that's the typical solution that we expect to get whenever we do d vector x over dt equal to a vector x. Then therefore imply that this big mess right here is what we call the particular solution. And this solution is unique to vector b, which is the reason why it involves vector b. Now, the big question then is, how is this formula come about? So let me show you a simple proof. Well, actually, not that simple to write out the entire proof, but I'm going to try to show you a proof. So the proof that I want to do is to kind of prove to you that the particular solution has to be in this form, because you already know the homogeneous solution, because that's basically what we learned back in 13.2. So what I want to do is want to prove to you that given d vector x over dt equal to a vector x plus vector b of t, the particular solution is e to the ta integral of, maybe I do this, is vector x sub p is equal to e to ta integral of e to negative ta b vector b of t dt, with the homogeneous solution given to be e to ta vector c. So that's essentially what we try to prove, is to try to prove that the particular solution is the way it looks, and therefore now I can combine that with the homogeneous solution and find out the answers. Now, it shouldn't be too hard to identify that the homogeneous solution is e to ta vector c. Oh, maybe I should write this. Because that's basically the whole premise of what we learned or tried to do back in 13.2, last section. But to be fair, let's just quickly show. So if you have vector x sub h being e to ta vector c, then if you take the derivative with respect to t of vector x sub h, that would just equal to the derivative of e to ta vector c, and that just basically equal to a e to ta vector c, which is basically a times vector x sub h. Therefore, that demonstrate, okay, just going to do this. That kind of demonstrate that has to be a homogeneous solution. So now the question is, how do I find the particular solution? So the way to find the particular solution is we will use a very simple technique that you learned called variation of parameters to solve for vector x sub p, the particular solution. So now I don't know how many of you remember the variation of parameters, but the way the variation of parameter works is that we would try to assume the particular solution is a multiple of the homogeneous solution, and then try to use that to solve for the new parameter. Okay, now maybe easier for me to just go along and explain to you. So we're going to assume that vector x sub p, the particular solution, is the homogeneous solution, which is e to ta. I don't need the c because the constant doesn't matter. Multiplied by some new function, which I'm going to call it vector u of t. And so that's basically what the variational perimeter is, because now I'm trying to actually not instead of solve for vector x of p, I'm going to try to solve for vector u. Because once I know what vector u is, I will then be able to multiply by e to ta to form vector x of p. So, but the question is, how is that better? Well, let's find out. So if that's what it is, I'm going to go and take the derivative with respect to t of vector x of p. That would just equal to me taking the derivative of e to ta vector u of t, which just so happen is a product between two things. A matrix and a vector, but since a vector can be considered as a one single column or single row matrix, I can presumably call this a product between two matrices. And I'm going to try to take the derivative of that, and therefore the product rule for matrix product rule for differentiation of product of matrices would now be applied. So therefore will be let's see what I wrote. The derivative of matrix A, so therefore in this case matrix A would be, so this is my matrix A of t, this is my matrix B of t. So therefore derivative of this will be A e to ta multiplied by B, which is vector u of t, plus, and then I will take e to ta, and then multiply by the derivative of vector u of t, which I'm going to call vector u prime of t. Now remember, this expression should equal to, based on our differential equation, based on a vector differential equation, should just equal to this thing with x sub p plugged into x. So therefore, now according to our differential equation, a times vector x sub p plus vector b of t should equal to a e to ta vector u of t plus e to ta vector u prime of t. And if you think about what is actually a times vector x of p, well, that technically is a e to ta vector u of t plus vector b of t equal to a e to ta vector u of t plus e to ta vector u prime of t. Notice that these two things just completely subtracted out, and therefore leave me with this equation. Vector b of t is equal to e to ta vector u prime of t. So now what I'm going to try to do is try to figure out what is vector u prime, because in this scenario right here, I'm going to try to solve for vector u, and once I have vector u, I can multiply that by e to ta to form vector x sub p, which is our particular solution. So what I'm going to do next is to multiply both sides by e to the negative ta, because e to the negative ta is the inverse of e to ta, and therefore give me vector u prime of t would equal to e to the negative ta vector b of t. And if that's what u prime is, then I can say if I integrate this thing, I should get u. And if that's what u is, then I can now say that vector x sub p would have to be e to the ta multiplied by integral e to negative ta vector b of t dt, as we said in the theorem. So now that we have this formula to find a particular solution, and we already know how to find the homogeneous solution using matrix exponential, now we can actually try to see if we can actually solve a non-homogeneous differential equation. So, and I hope this makes sense. if you look at what x sub p is, notice there's a lot of things going on. You have to multiply e to negative ta, so meaning you have to know what e to ta is first, by vector b. Once you multiply those two things together, you have to integrate this whole thing. And after you integrate this whole thing, you have to then multiply by e to ta. And that gives you the particular solution. Then you have to add that to the homogeneous solution to complete your problem. And remember, on top of that, you have to find e to ta first, which is kind of like the main focus in 13.2. So there's a lot of things here that you need to pay attention to and make sure you're done right. Otherwise, any one of those slight error could screw up your whole problem, particularly if you mess up your matrix exponential. It's literally have a ripple effect throughout the entire problem and screw up the rest of the problem. It can make a problem that would relatively work out very nicely into all of a sudden, like, things just don't work out and now you're stuck and you can't finish the problem. So please make sure you be very careful. And this whole question is difficult even for me because there's so many things going on and sometimes I make mistakes too. All right, let's try this example together. Let's try to solve this differential equation. D vector x over dt is equal to 1101 multiplied by xy plus e to t e to negative t. So first thing I like to do is to identify different parts. So this is my A, this is my vector B. And based on our theorems 13.3.2, vector x must equal to e to ta integral e to negative ta, vector b of t dt plus e to ta multiply some constant vector c. So how do we proceed with this thing? Well, lucky for us, we actually know the e to ta for this particular matrix 1101. We used that as an example back in 13.2. So if you take a minute to go back and look for it, you should be able to see it. So let me see if I can find it right now. So it's 1101. Nope. 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 Oh, right here. Oh, nope, that's not it. That's the eigenvalue matrix U. Oh, right here. 1101. And let's see what the matrix exponential is. The matrix exponential is e to t, t to t, 0, e to t. So that's what we're going to use. So good thing that we know that, so we don't have to go through the trouble of finding the, oops. Oh, there you go. Finding the e to ta. So in this case, we know that a equal to 1101. Then we know that e to ta, we found that out before, is e to t, t e to t, 0, e to t. So that's good. One less thing to worry about. So now let's try to, I guess we just go for it and see what happens. So therefore, vector x will equal to e to t, t e to t, 0 e to t, integral e to negative ta is the inverse of e to ta, and you can form the inverse by pretty much putting a negative in front of all the t. So therefore, it will be e to negative t e to negative t, 0 e to negative t. Multiplied by vector b, which is e to t, e to negative t, dt. And then plus e to the t, t to the t, 0 e to t, multiplied by some constant function, which I'm going to call c1, c2. So obviously, there's no easy part first. So this part right here, the end part, which is the homogeneous solution, will just be c1 e to t plus c2 t e to t, and then c2 e to t. So that's easy. Now let's do the difficult part. So here is vector x equal to, so I have to integrate before I can actually multiply the matrix e to ta on the outside. So I'm going to leave that one alone. I'm going to leave e to t, t to t, 0, e to t alone. I'm going to leave the integral because I'm not ready to integrate yet, but I can multiply this out. So if I do multiply this out, it becomes e to t times e to negative t, which is 1, minus t e to negative 2t. And on the bottom will be 0 times e to t plus e to negative t times e to negative t becomes e to the negative 2t. And so now what I'm going to do is try to integrate this. So notice that t e to negative 2t actually will require integration by parts. So I'll leave it up to you to actually do that and verify that you have the answer that I have. Okay? And yes, at this point, you should go ahead and look back and make sure you know how to do integration by parts so that you don't get caught up in doing this sort of problem and not knowing what to do. So if you do the integration by parts correctly, you actually should get t plus 1/4 e to negative 2t plus 1/2 t e to negative 2t. And on the bottom is easy, which is negative 1/2 e to negative 2t. And then I have this c1 e to t plus c2 t e to t. Oops. And c2 e to t. Oops, e to t. So now, what I have to do is multiply these two things together. So, it does look massive, but nothing much we can do, so we're going to go for it. So it'll be e to t multiplied by the top things right here. So it become t e to t plus 1/4 e to negative t plus 1/2 t e to negative t. And then I'll have t to t times negative 1/2 e to negative 2t become minus 1/2 t e to negative t. The bottom is easy. It's just 0 times the top plus e to t times 1/2, negative 1/2 e to negative 2t. So it becomes negative 1/2 e to the negative t. And then we still have this basic homogeneous solution right here at the end. And lucky for us, notice that these two terms just cancel out. And therefore, leave me with a rather simple expression. I'm going to write it this way. We'll write a c1 e to t plus c2 t e to the t plus t e to t plus 1/4 e to negative t. Actually, you know what? I'm going to put, actually it doesn't matter. I guess I'm just going to write it the way it is. I was thinking maybe I put e to negative t first and then put t equal to t at the end. But it's at the end, it really doesn't matter. And then what on the bottom, I would have c2 e to t minus 1/2 e to negative t. And I just simply want to line up the term. And if you don't want to, you can just put them together, which is okay. Do I want you to factor things out? I'm going to just say this is as good an answer for me, unless I specify that I want you to put into like vector form or something. Otherwise, I think that's good. All right. It's right now 28 minutes and 45 seconds, so I'm going to stop right here for today's video, and we'll continue on the next video. Okay, talk to you guys soon. Okay, bye bye.